Students, in this video, I'm going to teach you how to do Punnett square problems. Let me read to you what the definition of a Punnett square is. It says the Punnett square is a square diagram used to predict the genotypes of particular cross or breeding experiment. It is named after Reginald C. Punnett, who devised the approach. The diagram is used by biologists to determine the probability of an offspring having a particular genotype. These tables can be used to examine the genotypical outcome probabilities of offspring of a single trait, allele, or when crossing multiple traits from the parents. The Punnett square is a visual representation of Mendelian inheritance. So basically what this is, it's a tool that we know the genotypes of the parents and we want to find the probability or the chance of particular combination of genes. So these are kind of like word problems, so you do have to read them carefully and you do need to understand the terms homozygous dominant, heterozygous, and homozygous recessive. So I'm going to write them right here for you. So we're going to use the letter N. Remember, the alleles, the genes, are represented by letters. It's up to whoever comes up with the problems to determine the letter. Usually that has to do with the trait we're dealing with. So here we're dealing with normal skin versus albinism, and they use the first letter of normal, which is N. So let's use the letter N. So this is NN. This is homozygous dominant. Then we have big N, little n. This is heterozygous. Now, heterozygous can only be heterozygous. There's no such thing as heterozygous dominant or heterozygous recessive. Heterozygous just means they're different. We have the dominant and then we have the recessive. Very important to not make that mistake when talking about the genotypes. And we have the last one, which is homozygous recessive. So just remember, dominant would be the capital letter, recessive is going to be the lowercase letter. So here we have the scenario. Here we have our family that we've been talking about. We now know the genotypes of the parents, and we can, using the Punnett square, figure out how to, well, what are the chances that their future kids will have albinism or normal skin. So let me read the problem to you. It says a normal-skinned heterozygous man, big N, little n, is crossed with a normal-skinned heterozygous woman. Construct a Punnett square and write out the phenotypic ratios and genotypic ratios. Also describe the probability of having an albino child and a normal child. Probability refers to chance, which is written out as a percentage or as a fraction, which I'm going to go over right now. Normal skin is dominant, and little n, albinism is recessive. So if you read the other assignment, albinism follows a autosomal recessive. That means you need two of the defective genes to have the recessive trait, in this case albinism. Dominant means if you have one dominant gene, it masks the effects of the defective gene. So even though this man and this woman have the gene for albinism, their normal gene is enough to have normal skin. Really important to understand. And most of the time, the problems will tell you which one is dominant and which one's recessive. If it doesn't tell you, just the capital letter is dominant and the lowercase is recessive. So what you're going to do, you're going to put the genotypes of the parents on the sides of the Punnett square. Now, this is a mistake people do. You have to put the genotypes outside of the Punnett square. So let me do an example. So the man's genotype is NN, and the woman is also NN. So you have to put the genotypes of the parents here. Parent 1 and parent 2. Now, this is important. it doesn't matter if you put the mom's genotype here or the dad's genotype here or vice versa. You should get the same combination. So don't freak out about that. You have to put parent 1 and parent 2 on the sides of the Punnett square. Now, how you put the genotype is you put 1/2 of the genotype on the side of the Punnett square. So I'm going to put the dads here. This is dad. This is mom. I'm going to put dad right here. So his genotype is going to be N little n. Let me switch this color. And the mom's is also the same. She's heterozygous, so I'm going to put N. Do you notice that each side of the square only has one allele? Don't put 2 of them. It goes 1 here, 1 here, 1 here, and 1 here. All right? Now, all you're going to do next is you're going to combine the genotypes. Remember, it takes 2 genes to make 1 trait, at least in the beginning. So big N, inside I put big N, big N. Big N with little n, it's big N, little n. Little n with big N. It doesn't matter the order, but in all the problems, it's always going to be the capital letter first. Little n and little n combined together make 2 little n's. So did you notice? Usually that's why we're going to do it on paper. When I do these problems, when I used to do them, I would kind of use my pencil or pen and then combine them like this. Like, oh, this one with this one, this one with this one, this one with this one, and this one with this one. It's kind of similar to the FOIL method in math. You just combine the alleles together. This one with this one, this one with this one, this one with this one, and this one. All right. So this is what the possible genotype combinations we get from mom and dad. Now the questions are, you have to do a genotypic ratio. Now what does that mean? Can I change color? So genotypic ratio is going to be, a ratio is used to compare, mathematical comparison. So this is how the order it goes. So I'm going to abbreviate. It's going to be HD, homozygous dominant, heterozygous, I'll just put het for heterozygous, and homozygous recessive. You have to count how many homozygous dominants do I have, how many heterozygous do I get, and how many homozygous recessive do I have. So based off this combination, the genotypic ratio, I'll put here, genotypic ratio is going to be, I have one homozygous dominant. I have, how many heterozygous do I have? 1, 2. And how many homozygous recessives do I have? I only have 1. So my genotypic ratio is 1 to 2 to 1. There's 1 heterozygous dominant, 2 there's 1 homozygous dominant, 2 heterozygous, and 1 homozygous recessive. Then you're going to do the phenotypic ratio. Phenotypic ratio refers to the physical characteristic that the child is going to have. So let me put it down here. So phenotypic ratio. And how it is usually, or not ration, you know what I mean. Phenotypic ratio is going to be the dominant trait versus the recessive. So based off the information, normal skin is dominant. I have 1 normal skinned kid. I have another normal skinned kid, another normal skinned kid, and 1 albino child. So I have 1, 2, 3 3 normal skin children, and I have 1 recessive, homozygous recessive, which is 1 albino child. So the phenotypic ratio is going to be 3:1. 3 normal, healthy skinned individuals to 1 albino child. Hope this looks not, this kind of looks messy. The next one will be better. Probability. Probability. It's going to ask you for what are the chances. So you can think of each square as 25%. Or 1/4. So you got to know math for this unit. So if I were to ask you, what's the probability of having an albino child? It would be 25%. Or 1/4. So that means that if this couple has a child, the chance of having albinism is going to be 25% or 1/4. Now, what's the probability of having a normal child? 25 plus 25 plus 25, that is 3/4 as a fraction, and as a percentage is 75%. So for these problems, you got to know what's homozygous dominant, heterozygous, homozygous recessive. You need to know which one's dominant and which one's recessive in the characteristic to do these correctly. So what I'm going to do is I'm going to do one more. How exciting. And this is different. This is an albino man is crossed with an albino woman. Construct a Punnett square. Basically the same exact thing. So what I want you to do is I want you to pause the video right now. Well, not yet. And then try it on your own. Try to do the same ones. All right, pause it right now. All right, so let's do this one. You unpaused the video. So let's do, let's put the mom right here. And I'll just put blue for dad. That's not blue. And I combine them together. Oh, this one's easy. Genotypic ratio. Why keep ration? Remember, it's going to be HD to hetero to homozygous recessive. That's just going to be 0 to 0 to 1. Now, the phenotypic ratio is going to be dominant to recessive trait. In this case, normal skinned to albino. No normal skin. And how many albinos? 1, 2, 3, 4. 0 to 4. So this couple, if they were albino, albinos have only albino children based off this information. And what are the chances of having a normal kid? Oops. Normal. It's 0 out of 4 or 0%. What's the probability of having albino children? It's 4/4 or 1, which is equal to 100%. Remember, it doesn't matter if the mom goes here, especially in this one. I mean, they have the same genotype. All right, we're almost done. Let's do one more. All right, so this one is, so read it and then pause the video and then work it out. Okay, you unpaused. So it doesn't matter if dad goes here. Remember, one side has one allele, big N, big N, big N, big N. That one's easy. Remember, genotypic ratio is HD hetero HR. It's how many HDs do I have? 4. How many heteros? 0. How many homozygous recessives? 0. And the phenotypic is to dominant to recessive. And how many dominant do I have? We have 4 normal skin to 0 um, albinos. And the last one, what is the probability? Got lazy writing these out. Probability of a normal kid. Normal is going to be 4 out of 4. 1/4, 1/4, 1/4, 1/4, or 25, 25, 25. So 4 out of 4, or 100%. And probability of albino is none, 0 out of 4, or 0%. Common mistakes that students make is they put 2 letters here. It's only 1 gene per side, and they get confused of how to combine them. So for the purpose of this lesson, you should know how to set them up and how to read them. And hopefully, I wish I wrote better, but oh well. Okay, so that's going to be, we're going to practice these in class, and you're going to have a video to, not a video, a worksheet attached to this.